Stars can explode with the force of billions of nuclear bombs in seconds. These are stellar flares, sudden eruptions on distant stars that blast out energy across the entire spectrum. They shape space, weather, influence the fate of orbiting planets, and even determine whether alien worlds could ever support life. But recent observations have uncovered something strange. Flares are breaking the rules we thought governed them. They appear where they should not, behave in ways that defy our best models, and sometimes seem to come from nowhere. By the end of this video, you will know why these 25 oddest flare discoveries are forcing astronomers to rethink how stars truly work. How can a single flare ring a star like a bell? And why do some stars erupt with perfect clockwork timing, while others flare in wild storms? What would it mean if our own sun decided to break the rules? The Kepler Space Telescope uncovered something that should not exist. For years, astronomers assumed that only young or extremely active stars could produce truly massive flares. Younger stars spin faster, their magnetic fields churn wildly, and their surfaces erupt with far more violence than older stars like our Sun. But Kepler, which stared at hundreds of thousands of stars for years, found evidence that completely overturned that picture. It found Sun-like stars, middle-aged and quiet, unleashing flares up to 10,000 times more energetic than any solar flare ever recorded. Scientists called them superflares. At first, many researchers thought the data must be wrong. Maybe the star was not actually Sun-like. Maybe the flare was a glitch in the instrument. But careful analysis confirmed it again and again. Some of these stars looked nearly identical to our own Sun. They had similar rotation rates, similar surface temperatures, and similar chemical compositions. Yet every few hundred years, they would erupt with an energy equivalent to billions of hydrogen bombs detonating at once. This discovery created a deep puzzle for stellar dynamo theory. The dynamo is the internal engine that generates a star's magnetic field. In Sun-like stars, the dynamo is thought to be driven by a delicate dance between rotation and convection, the churning of hot plasma inside. A star that spins slowly, like our Sun, should have a relatively calm magnetic field. Yet these superflares suggest that even a quiet dynamo can sometimes muster enough energy for a catastrophic release. Something is missing from the models. Perhaps a sudden reorganization of magnetic loops deep within the star creates a kind of short circuit that unleashes enormous power. Or perhaps the star's magnetic field can occasionally store energy over centuries and then release it all at once. The implications for our solar system are unsettling. If our Sun is truly similar to those superflare stars, then it might be capable of producing an event that dwarfs anything recorded in human history. A superflare from the Sun could disrupt global power grids, disable satellites, and damage the protective ozone layer that shields life from ultraviolet radiation. These events are rare, but over geological timescales, a single superflare could reshape the habitability of Earth in ways we are only beginning to understand. It raises the question, has the Sun ever produced such a flare in the past? Evidence from ice cores and tree rings hints at past solar storms far stronger than any modern one, but nothing on the scale of a superflare. Still, the discovery forces astronomers to reconsider what is normal. Our star may not be as predictable as we once thought, and that sets the stage for more strange findings that keep rewriting the rulebook. Flares do not just shape stars, but also the worlds orbiting them. When a star unleashes a powerful flare, it sends a wave of high-energy particles and radiation hurtling into space. Any planet caught in that blast experiences something extraordinary. On Earth, we see aurorae when charged particles from the Sun interact with our magnetic field and atmosphere, creating shimmering curtains of green and red near the poles. But the aurorae triggered by stellar flares on distant exoplanets can be far more intense, sometimes bright enough for telescopes to detect from hundreds of light-years away. This discovery has turned flares into unexpected tools for studying alien worlds. Instead of being obstacles that make observations harder, flares now help astronomers probe the hidden magnetic fields and atmospheres of planets we cannot visit. One of the most striking examples involves a hot Jupiter called HD 209,458b. This planet orbits incredibly close to its star, completing a full year in just over 3 Earth days. That proximity means it is constantly bathed in the star's radiation and occasional flaring activity. When a flare struck this planet, the resulting auroral emission was so powerful that telescopes on Earth could see its signature in the spectrum of light coming from the system. The aurorae revealed something surprising. The planet has a strong magnetic field, much like Jupiter in our own solar system. This magnetic field acts as a shield, deflecting most of the stellar particles and channeling them toward the poles, where they produce intense light shows. By studying the way the auroral light changed in brightness and color over time, scientists could map the structure of the magnetic field and even estimate its strength. Before this discovery, measuring an exoplanet, its magnetic field was nearly impossible. Now, flares provide a natural probe. The implications go beyond just magnetic fields. As charged particles from the star slam into the planet's upper atmosphere, they also excite atoms and molecules there, causing them to emit specific wavelengths of light. This process reveals the composition of the atmosphere itself. In the case of HD 209,458b, the auroral emissions showed traces of hydrogen, oxygen, and carbon in the upper layers. But the data also suggested something unexpected. The atmosphere was eroding. The intense radiation and particle bombardment from the star were stripping away the planet's outer layers, slowly boiling it off into space. This gave astronomers a direct look at a process thought to shape the fate of many close-in exoplanets. Over millions of years, the constant attacks from stellar flares could transform a gas giant into a smaller rocky world, or even cause it to disappear entirely. The aurorae became a window into the planet's past and future. This method of using flares as probes is now being applied to other systems. Every time a flare erupts, it creates a brief but intense laboratory for studying the planets it illuminates. Astronomers are learning that the magnetic fields of exoplanets vary widely. Some are surprisingly strong, others are weak or even absent. A planet without a protective magnetic field would suffer far worse consequences from stellar flares, including a stripped-away atmosphere and destruction of any potential life. So the presence or absence of aurorae tells us whether a planet is safe or vulnerable. It also raises a deeper question. Could aurorae on distant exoplanets ever be visible to the naked eye from the surface of a nearby world? If you stood on a moon orbiting a gas giant with a flaring star, the sky might be ablaze with color, an unending light show powered by the fury of the star above. And that is just one more way these stellar outbursts continue to surprise us, revealing hidden details about planets we can barely see. The next discovery takes this idea even further, showing how flares can reveal things that are not even there. Some of the most powerful superflares do not come from where astronomers expected. For decades, the standard model of solar flares taught that the biggest eruptions require the biggest active regions. On the Sun, a single enormous sunspot group can stretch across hundreds of thousands of kilometers, storing vast amounts of magnetic energy. When that magnetic field becomes unstable, it snaps and releases a massive flare. Larger spots mean larger flares, and the largest flares come from the largest spots. That logic seemed straightforward, but when astronomers began analyzing thousands of stellar light curves from the Kepler telescope, they found something that broke the pattern. The most energetic superflares often arose from stars that did not have any single giant spot. Instead, their surfaces were covered in many smaller spots, arranged in clusters. These clusters were not simple. They had complex magnetic topologies, with fields twisting and tangling around one another like a knot of rubber bands. The interactions between these smaller spots produced flares that dwarfed anything our Sun has ever produced. It was as if a swarm of small magnets, when arranged just right, could unleash more energy than a single giant magnet ever could. This discovery forced a major shift in thinking. The traditional solar paradigm, where flare energy scales with spot size, might not apply to other stars. The key factor is not the size of the spot, but the complexity of the magnetic configuration. When multiple spots exist close together, their magnetic fields can merge, cancel, or reconnect in ways that release enormous amounts of stored energy. A cluster of small spots can create a network of magnetic loops that interlace and become unstable all at once. The resulting flare can be orders of magnitude larger than anything a single spot could produce. Statistical studies of Kepler data confirmed this pattern. Stars that showed many small spots across their surface, indicated by small but frequent dips in brightness, were far more likely to produce superflares than stars with a single large spot. The relationship between spot coverage and flare energy was not linear. It was a steep curve that only made sense when astronomers accounted for the interactions between spots. In some cases, clusters of perhaps a dozen modest-sized spots created magnetic topologies so tangled that they erupted with the energy of 10,000 solar flares. The implications are twofold. First, the Sun may be capable of producing superflares if its own spots ever arrange themselves into just the right kind of tangled cluster. Such an event would be rare, but not impossible. Second, it means that predicting stellar flares is far more complex than simply looking at the largest spot. Astronomers now have to model the entire magnetic landscape of a star, including the invisible connections between spots. The star's magnetic field can reorganize in surprising ways, sometimes slowly building up stress over months, then releasing it in a single catastrophic event. This is a humbling reminder that the Sun, our closest star, still holds secrets. We have been watching its spots for centuries, but we are only now beginning to understand the hidden dance that governs its most violent outbursts. Some flares are so extreme they briefly turn into fusion reactors. Inside a star's atmosphere, the temperatures and densities required to fuse atoms together are normally found only deep in the core, where crushing pressure and millions of degrees force hydrogen to become helium. But certain stellar flares can recreate those conditions high above the star's surface, in the outer layers where matter is usually thin and much cooler. When a flare releases an enormous amount of magnetic energy in a small volume, the plasma can be compressed and heated to tens of millions of degrees. At those extremes, atomic nuclei collide with enough force to overcome their natural repulsion, and fusion begins. This is not the sustained burn that powers the star's interior. It is a brief, violent burst, a tiny fusion reactor that ignites, burns for seconds, and then fades. Yet during that fleeting moment, it can synthesize elements that are rare or even absent in the star's normal composition. The most telling evidence comes from gamma-ray lines. When certain fusion reactions occur, they produce unstable isotopes that decay and release gamma rays at very specific energies. Observations of the most powerful solar and stellar flares have detected these telltale gamma-ray signatures, including lines from the decay of radioactive beryllium and lithium isotopes. Beryllium and lithium are fragile elements, easily destroyed inside stars, so their presence in a flare spectrum is a clear fingerprint of freshly synthesized material. The fact that they appear only during the most energetic phases of a flare and disappear quickly afterward confirms that they were created on the spot. This discovery has forced astronomers to rethink how stars enrich their surroundings. Normally, the heavy elements we see in the universe are forged inside massive stars over millions of years, then scattered by supernova explosions. But here, we have evidence that stellar flares, brief eruptions lasting minutes, can act as miniature nucleosynthesis factories. They produce small but measurable amounts of lithium and beryllium, elements that are notoriously difficult to create in the standard stellar fusion chain. Some researchers now suspect that, over billions of years, countless flares across the galaxy might have contributed significantly to the abundance of these elements in interstellar space. The idea blurs the line between two very different processes: a flare, which we think of as an explosive release of stored magnetic energy, and a fusion reactor, which we think of as a sustained nuclear burn. In the most extreme cases, these two phenomena merge. A flare becomes a transient star within a star, a place where the ordinary rules of the stellar atmosphere are suspended and a tiny pocket of creation opens up. The question then becomes, how common are these fusion flares? Do they happen on our own sun, or only on far more active stars? Evidence from the sun itself shows that even our relatively calm star can produce gamma-ray flares capable of fusing elements, though only during its strongest eruptions. That means our own sun has briefly become a fusion reactor, right above our heads, countless times throughout its history. And if flares on other stars can reach far higher energies, they could be producing not just trace amounts of lithium and beryllium, but also heavier isotopes, maybe even the raw materials for future planets. The discovery turns flares into active participants in the chemical evolution of the cosmos, not just passive events on stellar surfaces. It opens a new frontier in understanding where the elements around us truly come from. And that is far from the only way flares have surprised us. Some of them seem to stretch the very definition of what a flare can be, as we are about to see. Almost all flares send out X-rays and ultraviolet, but a rare kind erupts in visible white light. For decades, the standard model of a solar flare assumed that the energy released in the explosion stayed trapped in the chromosphere, the middle layer of the star's atmosphere. There, it heated plasma to millions of degrees, but that energy was thought to be converted mainly into high-energy radiation, not into light we could see with our own eyes. Then astronomers started catching something strange. During the most intense flares, a sudden surge of white light would appear, so bright that it could briefly outshine the entire star. It was as if a second, smaller sun had ignited on the surface. The first definitive observations came from the sun itself, during the famous Halloween storms of 2003. In late October and early November of that year, a series of solar flares erupted from a gigantic sunspot group. The largest of them, classified as an X-class flare, was so powerful that it saturated instruments on Earth-orbiting satellites. But what caught everyone off guard was that this flare emitted a brilliant flash of white light, visible even through simple solar filters. Amateur astronomers around the world saw it with their own telescopes, a sudden brightening that lasted for several minutes. The flare was not just violent in the invisible spectrum, it was literally shining in the daylight. This discovery forced a complete rethinking of how energy moves through a flare. In the old model, the energy released by magnetic reconnection was carried by high-energy electrons that streamed down into the chromosphere, where they dumped their energy as heat. That heat then produced intense X-rays and ultraviolet, but the deeper layers of the star, where visible light is normally produced, remained untouched. The white light emission proved that something extra was happening. Some of that energy was penetrating much deeper, down into the photosphere, the visible surface of the star. There, it heated the plasma to temperatures high enough to emit a continuous spectrum of light, the same kind of broad white glow that makes the sun appear yellow-white to our eyes. The mechanism is still debated, but one leading idea is that these electrons can sometimes be so energetic that they blast right through the chromosphere without being stopped. They carve a channel, a kind of energy river, that reaches the photosphere and deposits their energy in a matter of seconds. Another possibility is that a shock wave from the flare front pushes downward, compressing and heating the lower atmosphere. Whatever the exact process, the result is that for a few minutes, a patch of the star becomes millions of degrees hot enough to emit more visible light than the rest of the entire stellar disk. That is an astonishing thought. A single flare can outshine a star. The Halloween flare of 2003 had real-world consequences here on Earth. It disrupted satellite communications, caused power grid fluctuations, and even forced rerouting of some airline flights to avoid high radiation levels at polar altitudes. The white light flash itself did not cause those effects directly, but it signaled that the flare was carrying far more energy than typical events. It was a sign that the star had breached its own atmospheric barriers. And that raised a deeper question. If a flare can send energy all the way to the photosphere, what else might it be capable of? Because different wavelengths of light carry different information about a flare. X-rays tell us about the hottest plasma in the corona. Ultraviolet reveals the chromosphere's response. Radio waves track the accelerated electrons. But white light, especially the broad continuous spectrum, gives us a direct look at the very base of the flare, the spot where the star's visible surface gets hammered by the explosion. By studying white light flares, astronomers can measure how deep and how violent the energy transport really is. And the more we learn, the more we realize that flares are not just storms in the atmosphere, they are seismic events that can shake the entire star. A few flares produce flashes that rival the power of gamma-ray bursts from deep space. For decades, astronomers have studied gamma-ray bursts as the most energetic explosions in the universe, typically coming from distant galaxies where massive stars collapse or neutron stars collide. But they have also found something unexpected much closer to home. Certain stellar flares, especially those from a special class of star called a magnetar, can emit short, intense pulses of gamma rays that look almost identical to these cosmological beacons. The distinction matters because true gamma-ray bursts are cataclysmic events that mark the violent deaths or mergers of stars, while magnetar flares are only magnetic storms, but storms of almost incomprehensible scale. A magnetar is a type of neutron star, the collapsed core of a massive star that went supernova. Its magnetic field is billions of times stronger than anything we can produce on Earth, so powerful that it can distort the atomic structure of matter around it. When that magnetic field becomes unstable, it can snap and release a burst of energy in a fraction of a second. The most famous magnetar in our own galaxy is catalogued as SGR 1806-20. In December of 2004, this object, located about 50,000 light-years away, unleashed a flare so powerful that it briefly outshone the entire gamma-ray sky. The burst saturated detectors on several spacecraft and even affected Earth's upper atmosphere, causing a measurable disturbance in the ionosphere, despite originating halfway across the galaxy. In that mere tenth of a second, the magnetar released more energy than the Sun produces in hundreds of thousands of years. Astronomers were stunned because the gamma-ray signature was remarkably similar to the short gamma-ray bursts that often come from merging neutron stars in distant galaxies. For a moment, some thought a genuine cosmological gamma-ray burst had occurred inside the Milky Way, but careful analysis showed the difference. True gamma-ray bursts involve matter collapsing into black holes or ripping apart in cataclysmic collisions. Magnetar flares are purely magnetic, a sudden reconfiguration of the star's own field lines that accelerate particles to near light speed, producing gamma rays. The extreme mechanism required to produce such a flash involves the magnetar's magnetic field storing energy for decades or centuries and then unleashing it in a kind of giant magnetic earthquake. The field lines twist and break, releasing a wave of high-energy radiation that washes over the galaxy. This discovery bridges two normally separate fields of astrophysics. On one side, stellar astrophysics, which concerns the lives of stars and their magnetic activity. On the other side, high-energy astrophysics, which studies the most violent events in the cosmos. Magnetar flares sit squarely between them, showing that even a single dead star can briefly compete with the most powerful explosions the universe has to offer. And it raises a fascinating question. If a magnetar flare can mimic a gamma-ray burst, how many distant gamma-ray bursts might actually be magnetar flares from other galaxies? Astronomers are now sifting through thousands of detected bursts, separating cosmic cataclysms from stellar tantrums. Yet the very existence of these hybrid events reveals that the line between normal stellar activity and extreme high-energy phenomena is far blurrier than anyone expected. The magnetic field of a dead star can produce results that look nearly identical to the birth of a black hole, and that is not the only surprise waiting in the strange world of stellar explosions. Some of them whisper secrets in patterns that repeat, as if the star itself is keeping time. Radio waves reveal a hidden universe of stellar violence that no other instrument can see. For decades, astronomers assumed that a flare, by its very nature, would announce itself across the full electromagnetic spectrum. If a star erupted, it would brighten in visible light, flare up in X-rays, and send out a burst of radio waves all at once. The energy released in one wavelength should be roughly proportional to the energy in another, because they all came from the same magnetic explosion. That neat picture collapsed when sensitive radio telescopes began catching flares that appeared only in the radio band. These events showed no detectable increase in optical light, no surge in X-rays, nothing except a sudden, brief spike in radio emission. They were completely invisible to the vast majority of astrophysical instruments, and they existed only in the radio sky. The first convincing evidence came from surveys of M-dwarf stars, the smallest and most common stars in the galaxy. These red dwarfs are notorious for their energetic flaring, often producing massive outbursts that dwarf anything from our Sun. But when astronomers pointed the Very Large Array, a network of radio dishes in New Mexico, at a sample of nearby M-dwarfs, they caught something bizarre. Some of the stars produced powerful radio bursts that lasted minutes to hours, yet simultaneous observations in visible light and X-rays showed nothing unusual. The star appeared calm and steady, as if nothing had happened. Only the radio data revealed the truth. A full-blown flare was underway, but it was hiding from all the usual detectors. This discovery forced a major rethinking of how magnetic reconnection works. In the standard model, a flare releases energy by breaking and reconnecting magnetic field lines. That process accelerates charged particles, mostly electrons, which then stream along the field lines and slam into denser plasma, producing a cascade of radiation across all wavelengths. But if the radio emission is strong while the optical and X-ray signals are missing, something fundamental must differ. One leading explanation is that these invisible flares occur in a different magnetic regime, one where the particle acceleration is less efficient at heating the surrounding plasma. In other words, the energy goes primarily into accelerating electrons to very high speeds, but those electrons do not then collide with enough material to produce visible or X-ray light. Instead, they spiral along magnetic field lines and emit only in the radio band, a process known as synchrotron radiation. The resulting flare is a ghost, a magnetic storm that screams in radio but stays silent in every other language. Another possibility is that these flares happen in regions of the star's atmosphere where the density is extremely low, so the accelerated particles escape into space before they can interact with enough matter to generate visible light. The energy simply leaks away as radio waves, harmless to the star but detectable across interstellar distances. This idea is supported by observations of certain M-dwarfs that show long-lasting radio flares without any associated optical brightening, as if the magnetic explosion happened high in the corona, far above the visible surface. The implications go beyond just understanding the star itself. Radio-only flares could be far more common than we realize. If they are invisible to optical and X-ray telescopes, then surveys based on those wavelengths have been severely underestimating the true flaring rates of stars. For every flare we see in visible light, there might be several more hiding in the radio spectrum, silently shaping the space environment around their host stars. That matters because flares affect the atmospheres and habitability of orbiting planets. A planet around an M-dwarf could be bombarded by radio-only flares far more often than we thought, possibly altering its chemistry or stripping away its atmosphere in ways we never predicted. The discovery also raises a practical challenge for astronomers. To see the full picture of stellar activity, we can no longer rely on a single type of observation. We need to combine radio surveys with optical, ultraviolet, and X-ray data, and even then we might miss events that emit only in the radio band. The universe is full of flares that are essentially invisible, whispering their secrets in a frequency that most telescopes never even think to listen to. And that is only one more layer in the growing mystery of stellar explosions, because radio waves have also revealed something even stranger, flares that seem to pulse with a rhythm, as if the star itself is beating like a heart. Some flares do not just pulse with rhythm, they lock onto the beat of a distant world. Astronomers have discovered something almost unbelievable in the data from Kepler and other space telescopes. Certain stars show flare activity that repeats at the exact same interval as the orbital period of a close-in giant planet. It is as if the planet itself is triggering the flare, pulling the trigger every time it swings around its star. The first convincing case came from a system called HD 189733, a star orbited by a hot Jupiter that completes a full lap in just over 2 Earth days. When researchers plotted the timing of the star's flares against the planet's orbit, they found a striking pattern. The flares did not happen randomly across the planet's year. They clustered around a specific phase of the orbit, always about the same spot relative to the planet's position. The star was erupting exactly when the planet was at a particular point in its journey. At first, many scientists dismissed it as a coincidence. Flares are chaotic events that can happen for many reasons. But as more examples emerged from other systems, the pattern became too strong to ignore. In multiple cases, the flare timing lined up with the planet's orbit, not just once but repeatedly, system after system. Something was linking the two. The leading explanation is a phenomenon called star-planet magnetic interaction. The idea is that the planet, especially a hot Jupiter orbiting extremely close to its star, carries its own magnetic field. As the planet moves through the star's extended magnetic field, the two fields can connect. They form a kind of invisible bridge, a magnetic flux rope that stretches from the star's surface down to the planet. This rope acts like a channel, transferring energy and charged particles between the two bodies. When the planet reaches a particular orbital phase, often where the magnetic fields are most aligned or most stressed, the rope becomes unstable. It snaps, releasing a burst of magnetic energy that looks exactly like a stellar flare. But this flare was not triggered by the star's own internal magnetic activity. It was triggered by the planet moving through the star's magnetosphere. The evidence for this process comes from multiple wavelengths. In some systems, the periodic flares are strongest in X-rays, which matches the signature of magnetic reconnection. In others, they appear in radio waves, consistent with the spiraling of electrons along the flux rope. Careful modeling shows that the flare timing aligns with the planet's position relative to the star's magnetic poles, just as the theory predicts. But there is still controversy. Some researchers argue that the apparent periodicity could be a statistical fluke, especially in systems where flares are rare and the planet's orbital period is short. Others suggest that the flares might not be triggered by the planet at all, but instead by tidal interactions. A close-in planet raises enormous tides on the star, physically distorting its shape and potentially altering its internal flow of plasma. Those tidal stresses could trigger magnetic activity deep inside the star, which then erupts as a flare at a predictable phase of the planet's orbit. In that scenario, the planet is not directly connecting magnetically, but its gravitational pull is the hidden hand that sets off the explosion. Disentangling these two mechanisms is an active area of research. Observing the same system at multiple orbital phases and across different wavelengths can help. If the flare is caused by a true magnetic connection, it should produce a specific pattern in the radio emission, a certain polarization that reveals the direction of the magnetic field. If instead it is tidal, the radio signature would be different. So far, the data are tantalizing but not conclusive. The implications, however, are profound. If a planet can directly trigger flares on its star, then the star's flaring activity is not purely internal. It depends on the planets that orbit it. A migrating hot Jupiter, a giant planet that spiraled inward toward its star over millions of years, would have left a trail of magnetic interactions behind it. The history of the planet's migration might be written in the star's flare pattern. This offers a new way to study how planetary systems evolve. When astronomers see a star with flares that repeat at a fixed orbital phase, they can infer the presence of a planet they might not have detected any other way. The flares become a beacon, signaling the world that causes them. And it raises an even stranger question. Could a planet ever eject itself from its own system by repeatedly triggering flares that alter its orbit? The energy from a single flare is tiny compared to a planet's orbital momentum, but over millions of years, the repeated kicks from these synchronized flares might slowly push the planet inward or outward, changing its migration path. The star and its planet become a coupled system, their fates intertwined in ways we are only beginning to glimpse, and this is just one more strange discovery hidden in the light of distant stars, waiting to rewrite the story of how worlds are born and lost. When a star flares, the explosion shakes its entire body. This is not just a metaphor. Astronomers have discovered that the most powerful flares send real seismic waves rippling through the star, causing it to ring like a struck bell. The discovery began with our own Sun. In the 1990s, instruments aboard the Solar and Heliospheric Observatory detected subtle oscillations spreading across the solar surface after a major flare. These solar quakes looked remarkably similar to earthquake waves, with compression waves moving through the interior and surface waves traveling along the outer layers. For the first time, scientists realized that flares were not just atmospheric events. They could physically shake the star all the way down. The surprise came when the Kepler Space Telescope, designed primarily to find exoplanets, turned out to be an excellent stellar seismometer. Kepler measured the brightness of stars with extreme precision, capturing tiny changes that revealed vibrations in their surfaces. When a massive flare erupted on a distant star, astronomers noticed something odd in the data, a pattern of ripples that persisted for hours after the flare faded. These were starquakes, far more energetic than anything seen on the Sun. In some cases, the seismic waves carried more energy than the flare itself, hinting that the explosion had triggered a fundamental vibration mode of the entire star. The technique used to analyze these events borrows directly from heliosismology, the study of solar oscillations. By measuring how waves travel through a star, scientists can infer the density, temperature, and rotation rate of its interior layers. It is like using an earthquake to map the Earth's mantle, but on a stellar scale. The Kepler data allowed researchers to probe the internal structure of stars that were hundreds of light years away, simply by watching how they rang after a flare. One of the most unexpected findings was that the wave patterns often did not match simple models. The ripples were sometimes split into multiple frequencies, a sign that the star's interior was not uniform. In some cases, the waves revealed that the star had a rapidly spinning core, decoupled from its outer layers. This offered a direct measurement of differential rotation deep inside a star, something that was previously accessible only through theoretical models. The starquakes also showed that flares could excite global oscillation modes, meaning the entire star vibrated at its natural resonance frequency for hours or even days. This was astonishing because it implied that the energy from a relatively short-lived flare could couple into the star's global structure, not just its atmosphere. The mechanism behind this coupling remains a mystery. One theory is that the flare's blast wave pushes against the star's magnetic field, which then acts like a giant spring, transferring the impulse into the interior. Another idea is that the sudden heating of the corona creates a back pressure that drives acoustic waves down into the star. Whatever the exact process, the evidence is clear. A flare does not just end when the light fades. It leaves the star trembling, and those tremors carry information about the star's hidden layers. For astronomers, this opens a new window into stellar interiors. Previously, studying the inside of a star required long, continuous observations of its natural oscillations, a method that works best for bright, nearby stars. Flare-driven starquakes offer another path. They allow scientists to study stars that are too faint or too distant for traditional asteroseismology. Every large flare becomes a natural seismic experiment, sending waves through the star and revealing its internal structure in the process. It also raises a deeper question. If a flare can make a star ring like a bell, can the ringing in turn cause the star to flare again? Could seismic waves from one eruption trigger new magnetic instabilities elsewhere on the surface, starting a chain reaction? Some models suggest this might be possible, that starquakes could act as a trigger for subsequent flares, clustering eruptions in time. If true, it would mean that a flare is not just an isolated explosion, but part of a larger, interconnected system where the star's own vibrations feed back into its magnetic activity. The discovery transforms our understanding of what a flare is. It is no longer just a flash of light or a burst of particles. It is a seismic event that shakes the star from its core to its corona, leaving behind a pattern that reveals the very architecture of the star itself. And that is far from the only way flares have surprised us. Some of them have revealed the presence of things that should not exist, as we will see next. The same flares that shake a star can also strip away a planet's atmosphere. This discovery hits hardest for the smallest and most common stars in the galaxy, the red dwarfs known as M-dwarfs. These stars are cool, dim, and long-lived, which once made them ideal candidates in the search for habitable worlds. Their habitable zones, the region where liquid water could exist on a planet's surface, lie very close to the star. A planet orbiting there completes a year in just days or weeks. For years, astronomers dreamed that these worlds might be oases of life, quiet and stable around their small suns. Then the telescopes started watching them flare. M-dwarfs are notoriously violent. Their magnetic fields, churned by fast rotation and deep convection, unleash flares far more powerful and frequent than anything our Sun produces. A single flare from an M-dwarf can release 10 or even 100 times the energy of a solar flare, and they happen not just once a month, but sometimes several times a day. When such a flare erupts, it sends a blast of extreme ultraviolet radiation and high-energy particles hurtling toward any planet in its path. That planet's atmosphere, the fragile blanket of gas that might shelter life, suddenly finds itself under bombardment. The first direct evidence of this erosion came from transit spectroscopy. When a planet passes in front of its star, a tiny fraction of the star's light filters through the planet's atmosphere. Different gas molecules absorb specific wavelengths of that light, leaving a fingerprint. By analyzing that fingerprint, astronomers can measure the composition and even the height of the atmosphere. In systems with active M-dwarfs, they saw something alarming. During and shortly after a flare, the absorption lines of hydrogen, the lightest element, became dramatically stronger. That meant the planet's upper atmosphere was expanding, puffing up like a balloon as the flare's energy heated it. The hydrogen was escaping, literally boiling off into space. One of the most studied cases is the System TRAPPIST-1, a nearby M-dwarf with 7 Earth-sized planets. Several of those planets orbit squarely within the habitable zone. But observations with the Hubble Space Telescope revealed that the innermost planets are losing their atmospheres at a remarkable rate. The stellar flares, occurring almost daily, are constantly heating and stripping the upper layers. Over a few billion years, an Earth-like atmosphere could be completely eroded, leaving behind a barren, airless rock. The models paint a stark picture. A single flare might remove only a tiny fraction of the atmosphere, but the cumulative effect over millions of years is devastating. The erosion is especially efficient for hydrogen and helium, the lightest gases. But even heavier molecules like water vapor and carbon dioxide can be dragged along as the upper layers are blasted away. The planet's magnetic field offers some protection, but if the field is weak, or if the flares are frequent enough, the atmosphere simply cannot hold on. This creates a painful paradox. The very stars that offer the best chance for finding habitable zone planets, because they are small and common, may also be the ones that make those planets uninhabitable. A world could have the right temperature for liquid water, yet be bombarded so relentlessly that any ocean would evaporate and any atmosphere would vanish. The habitable zone becomes a ghost region, where conditions look promising from a distance but are lethal up close. The discovery has forced a major shift in how astronomers search for life beyond Earth. Simply finding a planet at the right distance from its star is no longer enough. They must now measure the star's flaring activity, its magnetic temperament, its history of outbursts. A star that flares too often may sterilize its own children. The search narrows to the quietest M-dwarfs, or even to stars a bit more like our Sun, even though those are rarer and their habitable zones are farther out. It is a sobering lesson in cosmic ecology. The fate of a planet is not written just in its orbit or its composition. It is written in the temper of its sun. And flares, once seen only as spectacular fireworks, are now understood as sculptors of worlds, capable of carving away the very air that life would need to breathe. This insight refines the entire quest, turning the search for habitable exoplanets into a hunt for stars that know how to keep their temper. But flares are not always destroyers. Sometimes they build, on young stars, still surrounded by the swirling leftovers of their own birth. A new kind of stellar outburst has been caught in the act of creating. These are not the atmosphere-stripping monsters we just saw. These are flares that sculpt matter itself, turning gas and dust into temporary structures that can be seen across the galaxy. The process begins in a protoplanetary disk, a vast rotating ring of gas and tiny solid particles that orbits a newborn star. Within this disk, planets are slowly assembling. Dust grains collide and stick together, growing into pebbles, then boulders, then eventually world-sized bodies. But the star at the center is still settling down, and it flares frequently. Those flares, when they erupt, do something strange. They inject an enormous pulse of energy directly into the disk. The blast of X-rays and ultraviolet light hits the tiny dust grains, which are often made of silicates, carbon, and ices. In an instant, the grains are heated to thousands of degrees. They vaporize. A puff of atomic gas, rich in silicon, oxygen, iron, and carbon, expands outward from the site of the flare. For a brief moment, a region of the disk that was filled with solid dust becomes a transparent hot gas. Then the plasma begins to cool. As it cools, the atoms recombine and form new molecules, then clump together into microscopic particles again. The dust recondenses, not as the same old grains, but as fresh material, sometimes with a different chemical composition or a different crystal structure than the original. This recondensed dust forms a temporary cloud that can block a significant fraction of the star's light. Telescopes have caught these events in action. The Spitzer Space Telescope, which observed in the infrared, was especially good at detecting the thermal glow from warm dust. In a few young stellar systems, Spitzer recorded sudden, dramatic brightenings in infrared light that lasted for weeks or months. Then the brightness faded, sometimes leaving behind a subtle dimming that persisted for years. The interpretation was clear. A flare had vaporized a patch of dust. The hot gas emitted strongly in the infrared, and then, as the gas cooled and recondensed, the newly formed grains scattered and absorbed starlight, causing a temporary dimming. Ground-based infrared telescopes have since confirmed these events in other young star clusters. One particularly well-documented case involved a star in the Orion Nebula region. Astronomers saw the star's infrared emission spike by a factor of 10 over a few days, then slowly decline over the following weeks. Simultaneous visible light observations showed the star becoming fainter, exactly as the model predicted. The flare had created its own shroud. These discoveries have profound implications for how planets form. The constant cycle of vaporization and recondensation, driven by flares, can change the size and composition of dust grains in the disk. Larger grains might be broken apart by the shock of the flare, while smaller ones might be welded together by the recondensation process. The chemical makeup of the dust can also shift. Some minerals that require high temperatures to form, like certain types of silicates found in meteorites, might be produced preferentially in flare-heated zones. In a sense, the flares are acting like a refinery, processing raw interstellar dust into more complex materials that eventually become the building blocks of planets. But there is a dark side too. If a flare is too frequent or too powerful, it might prevent dust from ever growing into planetesimals. The constant disruption could keep the disk in a state of arrested development, where particles are repeatedly destroyed and reformed but never get the chance to stick together into larger bodies. This could explain why some young disks seem to persist for unusually long times without forming planets, while others evolve quickly. The flare activity of the central star may be the hidden governor of the whole planetary nursery. So the same flares that can strip atmospheres from fully formed planets can also shape the raw materials of worlds not yet born. They are both destroyers and creators, depending on the context. And as we watch these tempestuous young stars, we are seeing the very process that decides which disks become solar systems and which remain eternal clouds of dust. The story does not end there, because some of these flare-created clouds have revealed something even stranger, as we will discover next. Some stars obey a schedule. For decades, astronomers assumed that stellar flares were fundamentally chaotic events, erupting without warning and without predictable timing. The Sun certainly behaves that way, its flares arriving in irregular clusters linked to its 11-year magnetic cycle, but with no precise repetition from one event to the next. Then the Kepler Space Telescope found stars that broke that rule entirely. These stars produce flares at nearly identical intervals, sometimes repeating every few days or every few weeks for months on end. The pattern is so precise that you could set a clock by them. The first well-documented case was a star catalogued as KC 9651060. Its light curve showed a series of flares that occurred almost exactly every 48 days, with a jitter of only a few hours. The recurrence was too regular to be a coincidence. Something was forcing the star to erupt at the same orbital phase over and over again. The discovery sent astronomers searching through the Kepler archives for similar behavior. They found dozens of candidates, including one of the most famous and controversial stars in modern astronomy, KC 8462852, better known as Tabby's star. This star had already gained notoriety for its bizarre, irregular dimming events, which some had speculated were caused by alien megastructures. But when researchers looked more carefully at its light curve, they also found a pattern of small, repeating flares. The flares occurred at intervals that matched the star's rotation period, suggesting that a persistent active region on the surface was rotating into view and then out again, producing a flare every time it faced Earth. But the timing was so precise and the flares so similar in shape that some scientists proposed a different explanation. A binary companion orbiting the star might be triggering the flares magnetically, exactly like the star-planet magnetic interactions we discussed earlier. In this scenario, the companion star, rather than a planet, would be locked in a magnetic dance with the primary, sending a burst of energy every time their fields align. The case of Tabby's star remains hotly debated. The repeating flares might be caused by a long-lived spot complex that simply produces frequent eruptions as it rotates, or they might be the signature of an unseen companion. But the broader pattern is clear. Clockwork flares are real, and they reveal something fundamental about the stars that produce them. One leading mechanism involves a rotating spotted region that is magnetically very active. If a star has a permanent or long-lasting cluster of spots, and that cluster happens to produce flares more frequently than the rest of the surface, then every time the star rotates, that region swings into view and the flares appear to repeat. The period of repetition is simply the star's rotation period. In that case, the flares are not truly periodic in the sense of being triggered by an external force, but they appear periodic because we only see them when the active region faces us. The other mechanism is more exotic. A binary companion, either a smaller star or a massive planet, could have its own magnetic field that becomes entangled with the primary's field at a specific point in the orbit. As the companion moves around, the magnetic tension builds and then releases in a flare at the same phase every orbit. This is essentially the star-planet magnetic interaction we discussed earlier, but scaled up to a stellar binary system. The evidence for this mechanism comes from systems where the flare period matches the orbital period of a known companion, not the star's rotation period. That distinction is crucial. If the flare period matches the orbit, it suggests an external trigger. If it matches the rotation, it suggests an internal pattern. Either way, the existence of these regularly repeating flares challenges the idea that stellar activity is purely random. It hints that there are underlying cycles, locked in place by the star's own rotation or by the gravitational and magnetic influence of a companion. For astronomers, this is a powerful tool. If a star shows clockwork flares, we can predict when the next one will occur. That allows us to point telescopes at exactly the right moment, catching the flare in action across multiple wavelengths. It turns a chaotic phenomenon into a scheduled event, a laboratory that we can observe repeatedly, and it raises a deeper question about our own sun. Could the sun ever produce a repeating flare pattern? It does not, at least not with the precision seen on these other stars. But if the sun's magnetic field were somehow locked into a stable, long-lived active region, it might. That is a sobering thought, because it means the sun's behavior is not the only template. Other stars show us that flares can be tamed into a rhythm, and that rhythm tells a story about the hidden magnetic relationships that shape a star's life. A single flare can physically slow a star down. This sounds impossible at first. A star weighs more than 1,000,000 Earths, and a flare is just a brief explosion on its surface. How could something so small change something so vast? Yet the Kepler Space Telescope caught it happening, and the discovery upends what we thought we knew about how stars spin. The key lies in angular momentum, the same force that makes a spinning ice skater speed up when she pulls her arms in. A star's rotation is determined by how fast its mass is spinning around its axis. When a flare erupts, it often launches a huge magnetic loop, a structure of charged particles and magnetic field lines that stretches thousands of kilometers above the surface. That loop is rooted in the star, and as it rises, it carries with it a tiny fraction of the star's angular momentum. When the loop eventually breaks and escapes into space, it takes that angular momentum with it, like the skater suddenly throwing a heavy weight away. The star loses a tiny bit of spin. The effect is minuscule for a single flare, but the Kepler data showed something measurable. Astronomers identified stars with clear rotation signals, a periodic dimming caused by a large spot moving in and out of view. They tracked the rotation period by timing that spot signal. Then a superflare hit. After the flare, the rotation period had changed, sometimes by a few seconds, sometimes by minutes. The spot itself might have been disrupted, but careful analysis showed that the period shift was not random. It matched the amount of angular momentum the flare's magnetic loop would have carried away. The star had literally changed how fast it spins because of a single eruption. This discovery has deep implications for how stars evolve over millions of years. Astronomers have long known that stars slow down as they age, a process called magnetic braking. The standard model says that a steady stellar wind carries away angular momentum gradually, like a slow leak from a spinning top. But flares show that the leakage is not always slow. It can happen in violent bursts. Each major flare accelerates the star's slowdown by a measurable amount. Over a star's lifetime, perhaps a few hundred massive flares could account for a significant fraction of its total spin down. That means magnetic braking is not a smooth, steady process. It is punctuated by dramatic events, sudden jerks that alter the star's rotation in discrete steps. The implications ripple outward. A star's rotation rate controls its magnetic activity and its flaring behavior. A star that spins faster produces more powerful flares, but those flares themselves slow the star down, reducing future activity. This creates a feedback loop. The more a star flares, the faster it slows, and the slower it becomes, the less it flares. The system is self-regulating, but in a way that depends on the history of individual eruptions. It also affects the planets. If a star suddenly slows down, its magnetic field structure changes, and the space, weather around those planets shifts. Habitability is not just about the star's average rotation, but about the timing and size of these jolts. The discovery turns the life story of a star into a series of small but significant revolutions, each flare leaving a permanent mark on the star's spin. And that raises a deeper question. Could a series of flares ever spin a star down so quickly that it slips out of synchronization with a close orbiting planet, breaking the magnetic connection that triggers further flares? The dance between star and planet becomes even more complex. What we once thought of as a steady, predictable process now looks like a chaotic series of adjustments. The star is not a static clock. It is a spinning world that gets nudged by its own explosions. Each flare leaves a faint fingerprint in the star's rotation, a tiny change that accumulates over eons. And that fingerprint can be read in the light curves of distant stars, telling us how magnetic storms have shaped their entire lives. A flare in our own galaxy sent a signal that looked like it came from across the universe. For years, astronomers had been puzzled by fast radio bursts, incredibly brief but powerful flashes of radio energy that seemed to originate from distant galaxies. They lasted only milliseconds, yet carried as much energy as the sun releases in days. No one knew what caused them. Some theories pointed to mergers of neutron stars, others to collapsing black holes or alien technology. Then in April of 2020, a satellite called the Neil Gehrels Swift Observatory detected a burst of X-rays and gamma rays coming from a familiar source, a magnetar named SGR 1935 plus 2154, located about 30,000 light-years away in the constellation Vulpecula. Almost simultaneously, radio telescopes on Earth, including the Canadian Hydrogen Intensity Mapping Experiment and the Survey for Transient Astronomical Radio Emission, caught a fast radio burst coming from the exact same location. It was the first time such a burst had ever been traced to a source inside the Milky Way. This was not a random coincidence. The radio burst, catalogued as FRB 200428, arrived at Earth just milliseconds after the X-ray and gamma-ray flash. The timing and the location matched perfectly. For the first time, astronomers had direct evidence that fast radio bursts could be produced by magnetar flares. The discovery linked two fields of astronomy that had long seemed separate: stellar flaring activity and extragalactic radio transients. It showed that the same magnetic reconnection that drives ordinary stellar flares, when scaled up to the extreme environment of a magnetar, can produce a phenomenon that rivals the most mysterious signals in the universe. But there was a strange twist. The radio burst was hundreds of times brighter than any radio pulse ever recorded from a magnetar before. Normal magnetar radio emissions are relatively faint, detectable only with sensitive instruments. This burst was so powerful that it saturated some receivers. It was as if a firecracker had suddenly exploded with the force of a bomb, without any obvious change in the underlying mechanism. Why was this flare so much louder in radio than all the others? The leading explanation involves the geometry of the magnetic field. In a typical magnetar flare, the energy is released in a chaotic tangle of twisted field lines, and the radio emission emerges in a wide spray. But in this case, the reconnection event may have been unusually concentrated, funneling the accelerated particles into a narrow beam that pointed directly at Earth. That beam focused the radio energy into a tight cone, making the burst appear far brighter than it would have if it had spread out in all directions. This idea is supported by the fact that FRB 200428 was accompanied by a strong X-ray component, but the radio pulse was extraordinarily bright only in a specific frequency range. The beam was narrow, and we happened to be inside it. Another possibility is that the flare itself was fundamentally different. It might have involved the reconnection of magnetic field lines in a region with an exceptionally high density of plasma, amplifying the radio emission through a process called coherent emission. In coherent emission, particles move together in phase, like a marching band, rather than randomly, and their combined radio waves add up constructively, producing a much stronger signal than expected from the sum of individual particles. This is the same mechanism that powers pulsar radio beams, but on a far shorter timescale. the discovery forced a re-evaluation of how many fast radio bursts from other galaxies might actually be magnetar flares. If a single magnetar in the Milky Way could produce a burst powerful enough to be detected across the galaxy, then magnetars in other galaxies could certainly produce bursts detectable across cosmic distances. Some estimates suggest that a significant fraction, perhaps tens of percent, of all extragalactic fast radio bursts could come from magnetar flares rather than from exotic events like neutron star mergers. The key difference is that true extragalactic bursts are often one-off events that never repeat, while magnetar flares can repeat irregularly. But in our own galaxy, the magnetar SGR 1935 plus 2154 has produced multiple radio bursts since 2020, though none as bright as the first. This tells us that magnetars can produce a range of burst energies, and the brightest events are rare. The discovery also raised a new mystery. Why do some magnetar flares produce such bright radio emission, while most do not? The answer may lie in the magnetic field strength and the geometry of the reconnection site. Magnetars have fields that are 1,000 times stronger than ordinary neutron stars, and the way these fields snap and realign may occasionally create the perfect conditions for a narrow, bright radio beam. Understanding these conditions is now a major goal for astronomers. They are monitoring magnetars with radio telescopes, hoping to catch another such event and study it in detail across multiple wavelengths. Each detection refines the models, bringing us closer to understanding the full spectrum of stellar flare activity, from the quietest hiccups on the Sun to the most violent eruptions that can light up the galaxy. And the journey is far from over, because even as we learn to link fast radio bursts to flares, another strange discovery has been hiding in the same data, waiting to be noticed. For decades, astronomers assumed a flare rose and fell like a single wave. A simple magnetic loop would snap, release its energy, and the light curve would trace a clean, smooth peak followed by a gradual decay. This model worked well for the Sun, where flares often appear as isolated events, but high-cadence observations with the transiting exoplanet survey satellite, known as TESS, changed that picture completely. TESS stares at large swaths of the sky, measuring the brightness of stars every 2 minutes, sometimes even every 20 seconds. With that incredible time resolution, astronomers began to see that many stellar flares do not follow a simple pattern at all. Instead of a single peak, their light curves show multiple spikes, sudden dips, and long asymmetrical tails that stretch out in strange shapes. Some flares appear to have 2 or 3 separate bursts within a single eruption, each one occurring minutes or even hours apart. Others show a rapid rise, a quick plateau, then another rise, as if the star was gathering its energy and then releasing it in stages. These complex morphologies cannot be explained by a single magnetic loop arcade, the classic picture of a loop that breaks and reconnects in one clean stroke. The shapes demand something far more tangled. The leading explanation involves twisted flux ropes, enormous bundles of magnetic field lines that have become wound up like a rope under tension. When such a rope becomes unstable, it does not simply snap everywhere at once. Instead, it can erupt in a series of partial failures, each release triggering a new burst of energy. Sometimes a filament of cooler plasma, suspended above the star's surface by the magnetic field, gets launched outward. As it rises, it can stretch and twist the field lines further, causing additional reconnection events at different heights or locations. The result is a flare that unfolds over hours, with multiple peaks and asymmetric shapes that reflect the complex internal structure of the erupting magnetic field. Observations from TESS have shown that these complex flares are surprisingly common, especially on active stars. In some systems, as many as half of all flares display multiple peaks or clear asymmetries. That means the simple loop model, while useful for the Sun, is far too simple for many of the stars in our galaxy, and this has direct consequences for any planets that happen to be orbiting those stars. A flare with a single peak sends out a brief, intense pulse of radiation, but a complex flare with multiple peaks spread over many hours delivers a prolonged bombardment. The energy does not arrive all at once. It comes in waves, each one potentially affecting the planet's atmosphere, magnetic field, and chemistry in a different way. Worse, if the flare also launches a coronal mass ejection, a giant cloud of magnetized plasma, the timing of that ejection relative to the multiple peaks becomes unpredictable. Space weather around such a planet would be chaotic, with sudden jolts of radiation followed by lulls and then more jolts, stretching far longer than a single event. For an Earth-like planet, the consequences could be severe. The prolonged exposure could strip away more atmospheric gas than a single, sharp burst. The repeated heating could drive complex chemical reactions, altering the composition of the atmosphere in ways that are hard to anticipate. And if the flare's complex structure is caused by multiple reconnection sites spread across the stellar surface, then the radiation would hit the planet from slightly different angles over the course of hours, subjecting different hemispheres to different conditions. Astronomers are now trying to classify these complex flares into types, hoping to find patterns that predict their behavior, but the diversity is staggering, and each new TESS observation seems to reveal a shape that does not quite fit the existing categories. What is clear is that the simple picture of a magnetic loop breaking is only the beginning. The real story is one of tangled fields, twisting ropes, and multiple explosions happening in a chain reaction. And that means any planet in the path of such a flare faces a space weather event far more unpredictable than anything we experience from our own Sun. The next challenge is to figure out how common these complex flares are on Sun-like stars, and whether our own star ever produces them, because if it does, the lessons we learn from distant worlds may one day help us prepare for a storm we cannot see coming. A flare alone is only half the story. What follows can be far more dangerous: a colossal cloud of magnetized plasma, ripped from the star's atmosphere and hurled into space at speeds that defy imagination. The Sun produces these clouds, called coronal mass ejections, or CMEs, about once a week during its active years. They carry a few billion tons of matter and travel at around 1,000 kilometers per second. But on other stars, the scale is utterly different. Astronomers have detected CMEs from stellar flares that launch not billions, but trillions of tons of material, and at velocities exceeding 3,000 kilometers per second. That is fast enough to cross the distance between Earth and the Moon in about 2 minutes. These hyper-CMEs are the true heavyweights of stellar violence, and they are rewriting everything we thought we knew about how magnetic eruptions work. Detecting these giant ejections is not straightforward. A CME is a cloud of charged particles and magnetic fields, which makes it nearly invisible in normal light. But as it plows through the star's outer atmosphere and into the surrounding stellar wind, it creates a shock wave. That shock wave accelerates electrons, which then emit radio waves at a very specific frequency that drifts lower over time. These are called type Roman II radio bursts, and they act like the sonic boom of the eruption. When radio telescopes catch a type Roman II burst that persists for many minutes and sweeps through a wide range of frequencies. It tells astronomers that a massive CME is racing outward. Another telltale sign is coronal dimming. When a CME rips away from the star, it leaves behind a region of the lower corona that has been emptied of hot plasma. That patch becomes temporarily fainter in X-ray and extreme ultraviolet light. Telescopes that monitor stars at these wavelengths can see a sudden, localized drop in brightness just after a large flare, a direct fingerprint of material that was pulled away. The most extreme example so far came from a star called EV Lacerta, a small but furious red dwarf only 16 light-years away. In April of 2008, a powerful flare erupted on its surface. Space-based X-ray telescopes caught the initial flash, and ground-based radio observatories recorded a Type Roman II burst that indicated a CME moving at more than 3,000 kilometers per second. The mass expelled was estimated at over 100 trillion tons, enough to fill the Sun's entire inner solar system many times over. That is 1 million times more massive than any CME ever recorded from our own star. And EV Lacerta is not unique. Surveys of active stars have found similar signatures in dozens of systems. The common thread is that the fastest and most massive CMEs always come from the most magnetically active stars, especially those that are younger, smaller, or more violently flaring. These hyper-CMEs pose a direct threat to any planets in their path. A cloud of magnetized plasma moving at thousands of kilometers per second carries an immense amount of kinetic energy. When it slams into a planet's magnetic field, it compresses that field violently, sometimes pushing it all the way down to the planet's surface. This can strip away the upper atmosphere, drive away protective ozone layers, and even induce powerful electrical currents in the ground. On Earth, the strongest solar CMEs have knocked out power grids and disrupted satellites, but they are a minor inconvenience compared to what a hyper-CME could do. A planet around a flaring M-dwarf could be hit by such an event every few months or even more often. The cumulative effect over geological time could erode an atmosphere completely, turning a potentially habitable world into a barren rock. But here is where the mystery deepens. The standard models of magnetic eruption forces cannot easily explain how stars launch such massive CMEs. In the Sun, the energy for a CME comes from the magnetic field in the corona, and the mass of the ejection is limited by the density of material available in that region. A CME the size of those seen on other stars would require a much denser and more extensive magnetic structure. Some theories propose that the fast rotation and deep convection in active stars generate enormous magnetic flux ropes, bundles of twisted field lines that can store far more energy than anything on the Sun. When those ropes snap, they can lift a huge volume of plasma from deep within the star's atmosphere, not just the outer layers. This idea is supported by computer simulations, which show that a twisted flux rope can become unstable and erupt, dragging up material from lower, denser altitudes. The resulting CME carries far more mass than a simple solar-like eruption. Other researchers argue that the detection methods might be overestimating the mass. The Type Roman II radio burst technique relies on assumptions about the density of the stellar wind and the shock geometry. If those assumptions are wrong, the actual CME could be smaller. But the coronal dimming signals are harder to dismiss. When a patch of the star's corona fades by a significant amount immediately after a flare, it strongly suggests that a substantial amount of plasma has been removed. Multi-wavelength observations, combining radio, X-ray, and ultraviolet data, are now being used to cross-check these estimates. The early results suggest that hyper-CMEs are real, but may be rarer than the radio data alone imply. Regardless of the exact numbers, the existence of these colossal ejections forces a fundamental rethink. The Sun is a tame star by comparison, and yet we know that a single major CME can disrupt our technological civilization. Imagine a star that releases such events 100 times more massive and 100 times more often. The space weather around those stars is not just stormy. It is catastrophic, and as we search for planets that might harbor life, we must now ask not only whether a star flares, but whether its flares launch hyper-CMEs that could sterilize an entire world. The models of magnetic eruption forces are being challenged to explain how stars can eject so much matter so quickly. Some simulations now suggest that the key factor is the star's rotation. Rapidly spinning stars generate a dynamo that produces stronger and more complex magnetic fields that can support much larger flux ropes. When those ropes erupt, the energy released can easily exceed what we see in the Sun. The question now is whether our own Sun could ever produce such an event, or whether it is forever limited by its slower spin. The answer may determine the long-term habitability of Earth itself. And that is a question that keeps astronomers scanning the skies, looking for the next sign of a star that has lost its grip on its own atmosphere. Some stars wear the same dark spots for years, never fading. On the Sun, sunspots appear, grow, and then dissolve over weeks or months, vanishing as magnetic fields rearrange themselves. But certain stars show patterns that completely break that rule. In their light curves, captured by the relentless stare of the Kepler telescope, astronomers found a regular, repeating dip in brightness that did not change shape or depth over hundreds of days. The same spot, the same size, at the same location on the star's surface, persisted for years at a time. That alone was strange enough. Then the flares started to tell a deeper story. When a flare erupted on one of these stars, it often happened at the exact same spot where the persistent dark patch sat. And when the star's total brightness was averaged over long periods, that region appeared to be emitting a faint, constant glow in certain ultraviolet or X-ray wavelengths, even when no obvious flare was happening. It was as if the spot itself was always simmering, always releasing a low level of magnetic energy, a steady background fire that never went out. The only explanation is that the magnetic field anchoring that spot is extraordinarily stable. On the Sun, magnetic fields are restless. They emerge, twist, and cancel out, constantly changing. But on these stars, the dynamo that generates the magnetic field seems to have settled into a fixed pattern, perhaps locked in place by the star's rapid rotation. In rapidly rotating stars, the dynamo often reaches a state called saturation, where the magnetic field strength stops increasing even if the star spins faster. In that saturated state, the field may become more organized and less prone to the chaotic reconfigurations that make sunspots fade. Instead, the field concentrates into a few huge, stable patches that persist for years or even decades. Those patches are the permanent star spots. Every time the star rotates, the spot comes into view and the star's light dips slightly. But more than that, the spot is a magnetically active zone that continually releases small eruptions, a kind of persistent, low-grade flaring. When a larger flare occurs, it tends to happen right there, in that same stable magnetic structure, because that is where the energy is stored. So the star's overall emission in high-energy wavelengths never quite drops to zero. There is always a small contribution from that permanent spot, a background hum of magnetic activity that never sleeps. this discovery changes how we think about stellar magnetic cycles. The Sun has an 11-year cycle, with spots waxing and waning, but these stars appear to have no cycle at all, or at least not one that changes the spot pattern. They are stuck in a permanent state of high activity, with a magnetic field that is both strong and immobile. For any planet orbiting such a star, the consequences are profound. The constant background emission from the permanent spot means that planet's atmosphere is always being gently irradiated, even between flares. That steady input of high-energy radiation can gradually alter atmospheric chemistry, slowly stripping away lighter gases or driving haze formation. And when a larger flare does erupt from that same spot, it hits the planet from the same direction every time, pounding one hemisphere repeatedly over years. The planet never gets a break. The star's magnetic field has become a fixed engine of slow, relentless erosion. The puzzle now is why the Sun does not behave this way. Our star's dynamo produces a fluctuating field, not a stable one. Perhaps the Sun spins too slowly to enter that saturated state, or perhaps its convection zone is structured differently. But the existence of these permanent star spots shows that stable magnetic fields are possible in stars, and that the Sun's restless nature is not the only option. Someday, if we find a star with such a stable spot and a planet in the right orbit, we may have found a world where the sky always glows faintly from a permanent aurora, a constant reminder of the magnetic giant sitting quietly in the sky, never quite asleep, never quite awake. Not all stars lock their spots in place forever. Some obey a rhythm as predictable as the seasons, a magnetic cycle that rises and falls over years or decades. Our own Sun follows such a beat, an 11-year oscillation where sunspots appear in increasing numbers, then fade away as the magnetic field reverses polarity. Astronomers long assumed that every star with a magnetic dynamo would show a similar pattern, but the long-term data from the Kepler Space Telescope revealed a much stranger reality. When scientists sorted flares by their star's activity level, they found that the statistics of flaring, how often flares occur and how much energy they release, change dramatically over the course of the magnetic cycle. On some stars, flares become far more frequent and powerful during the peak of the cycle, exactly as expected, but on others, the pattern flipped entirely. The flares reached their greatest intensity when the star's surface had the fewest spots, when the magnetic field appeared weakest. That antiphase behavior defies every model of how magnetic energy is stored and released. It suggests that the deeper magnetic structure, invisible beneath the star's surface, can store energy separately from the surface spots, and that energy emerges as flares at precisely the wrong moment. Even more puzzling, Kepler found stars that show no cycle at all, despite producing obvious flares year after year. Their spots come and go, but without any regular pattern. The magnetic field seems to wander, never settling into a stable oscillation. Some of these stars may have extremely long cycles that outlast the few years of observation, decades or centuries instead of years. Others may have a dynamo that is simply chaotic, never locking into a rhythm. The discovery forces a new question: is the Sun's reliable cycle the exception rather than the rule? Most stars in the galaxy may beat to a different, less predictable rhythm, and the flares that shape their planets follow that hidden, uneven pulse. Binary stars reveal an even stranger trigger for flares. In systems where two stars orbit each other closely, the flaring rate can skyrocket far beyond what either star would produce alone. The culprit is the stellar wind, the constant stream of charged particles that every star blows into space. When a companion star's wind slams into the magnetic field of its neighbor, it does not just pass by, it compresses and distorts that magnetic field, sometimes triggering a magnetic reconnection event that erupts as a flare. The effect is strongest in close binary systems known as Rs Canum Venaticorum variables, or RSCVN systems for short. These are pairs of stars that orbit so tightly that one star's outer atmosphere practically grazes the other. As the companion moves through its orbit, its wind sweeps across the primary star's surface like a cosmic pressure wave. When that wind hits a region where the magnetic field is already stressed, it can push the system past the breaking point, unleashing a flare far bigger than the primary star's own internal dynamo could produce on its own. The most dramatic example comes from the binary system known as Lacertae. This pair of stars completes an orbit in less than 2 days, and radio and X-ray observations have caught flares erupting at nearly the same orbital phase every time. The wind from one star hits the other at a specific point in its journey, and like clockwork, the flare follows seconds or minutes later. The pattern is so precise that astronomers can predict when the next outburst will occur based solely on the orbital position of the companion. This discovery upends the idea that flares are purely internal events driven by the star's own magnetic field. Instead, the flaring can be externally forced, synchronized to the beat of the binary dance. Strangely, some RSCVN systems show flaring even when the wind from the companion should be too weak to matter. The wind density is low, and the magnetic field of the primary is strong, so the compression should be negligible. Yet the flares still come at the right time. This suggests that the wind is not just pushing on the magnetic field directly, but is seeding the star's own magnetic loops with extra charged particles, making them more unstable. The wind acts like a spark plug, not a battering ram. For any planets orbiting such a binary, the space weather becomes a nightmare of double intensity. They face not only the primary star's own flares, but also those triggered by the secondary's wind. The flaring follows a binary rhythm, pounding the planet at regular intervals, never giving the atmosphere a full chance to recover. The discovery shows that in the crowded environment of a binary system, a star's temperament is not its own. It is dictated by the invisible wind of its partner, a force that can turn a quiet star into a tempest, all because of a companion that may be too dim to see. And that raises a haunting question. Could our own sun have a companion, a dim star, or a massive planet, whose wind subtly triggers flares we never suspected? Some astronomers have searched for such a companion, but so far, none has been found. Still, the lesson from RSCVN systems is clear. In the universe, flares are not always born alone. They can be summoned by a partner, a ghost in the machine of gravity and wind. One flare can briefly outshine the entire star that spawned it. That is not a metaphor. In the archives of the Kepler and TESS space telescopes, astronomers have found light curves where a star suddenly grows tens of times brighter in total, not just in a small patch, but across its whole disk. The jump is so dramatic that the normal star, normally a steady point of light, becomes a temporary beacon that rivals the brightest stars in the sky. The flare does not just add a few percent to the star's light. It multiplies the star's entire output by 10, 20, sometimes even 50-fold for a few minutes. This defies every simple energy budget estimate. To make a whole star shine that much brighter, the eruption cannot be confined to a single active region. The energy must be spread across the entire surface, or the mechanism must somehow cause the entire visible disk to emit more light at once. How could a single magnetic explosion achieve that? One possibility is a giant prominence eruption. Prominences are huge loops of cooler plasma suspended above the star's surface by magnetic fields. They can be enormous, stretching across hundreds of thousands of kilometers. When such a prominence becomes unstable, it can collapse and slam back into the star, releasing its gravitational energy as heat and light. If that prominence is big enough, it might cover a significant fraction of the star's visible hemisphere, causing a sudden brightening that looks like the entire star is flaring. Another scenario involves an extreme coronal mass ejection that strips away the star's outer atmosphere, exposing hotter, denser layers underneath. Normally, the star's visible surface is the photosphere, a relatively cool layer. But if a powerful eruption blows off the corona and upper chromosphere, the deeper, hotter layers become visible. Those layers emit far more light per unit area, so the star appears to brighten globally. The effect is like peeling off the skin of a fruit to reveal the glowing flesh beneath. Observations of the most extreme superflares, like the one catalogued from the star KC 9651060, show a rise time of just a few minutes and a decay that stretches for hours. The total energy released in visible light alone can equal the star's normal output for an entire day. That energy must come from somewhere, and the only plausible reservoir is the star's global magnetic field, which can store energy over years and then release it in a single catastrophic event. The discovery suggests that stars can undergo a kind of magnetic breakdown, where their entire outer layers become involved in a reconnection event. This is far beyond the local flares we see on the Sun. These are storms that shake the star to its core, and they happen only rarely, perhaps once every few centuries or millennia for a given star. But when they do, the star briefly becomes the brightest object in its neighborhood, a temporary lighthouse that could outshine all its planets combined. For any world caught in the path of such a flare, the consequences are hard to imagine, but the light curve itself is a warning written in the star's own glow, a reminder that even the most steady sun can sometimes forget its calm. But amid these cataclysmic energies, something impossibly fragile appears in the spectra. When astronomers aim powerful ultraviolet and optical telescopes at a stellar flare, they expect to see the signatures of hot, ionized gases, atoms stripped of their electrons, plasma at millions of degrees. That is the language of a magnetic explosion, so it came as a complete shock when they started finding the fingerprints of molecules, not just any molecules, but simple ones like hydroxyl, which is a hydrogen and oxygen pair, silicon monoxide and titanium oxide. These are the same types of compounds that form in the atmospheres of cool stars and even in the gas clouds where planets are born. They should never exist inside a flare. The ultraviolet radiation and the extreme heat should tear them apart in microseconds, shattering their chemical bonds and leaving only isolated atoms. Yet there they are, clear and unmistakable, appearing and then fading over the course of minutes. How do they survive? The leading idea involves cool condensations. A flare is not a uniform ball of fire. It is a complex, turbulent structure with enormous temperature variations. Some regions within the flare may escape the full force of the heating. As the magnetic reconnection releases energy, it can also launch dense knots of cooler plasma that are briefly shielded from the worst of the radiation. These knots act like tiny shields, protecting the molecules long enough for telescopes to detect their spectral lines. The molecules might even be created fresh in those pockets, as the cooling plasma recombines and atoms form new bonds in the aftermath of the initial blast. Another possibility is that the molecules are not formed in the flare at all, but are lifted up from the star's lower atmosphere. In the photosphere, where temperatures are much cooler, molecules like titanium oxide are common and stable. A powerful flare could act like a massive scoop, pulling up material from those deeper layers and injecting it into the corona. The molecules would then be exposed to the flare's radiation, but they might survive for a short time before being destroyed. Their presence in the spectrum would be a direct fingerprint of material dredged up from the star's hidden depths. This creates a profound puzzle. The survival time for a molecule in a million-degree plasma is measured in seconds at most. Yet the observed molecular lines sometimes persist for tens of minutes. That means the molecules are either being continuously replenished or are confined to regions that are far cooler than the rest of the flare. Some models suggest that the flare's magnetic field can create isolated filaments of dense, cool gas that are magnetically insulated from the surrounding inferno. These filaments are like tiny oases in a desert of fire, and they can preserve molecules for surprisingly long periods, but the details are fiercely debated, and every new observation seems to deepen the mystery. The discovery forces astronomers to think of flares not as simple explosions, but as layered environments, where hot and cold coexist in ways that our models cannot yet fully explain. And it raises an even deeper question. If molecules can survive in the heart of a stellar flare, what other unexpected chemistry might be happening there? Could flares be places where complex organic molecules are briefly assembled, only to be destroyed moments later? The search for answers is driving a new generation of high-resolution, ultraviolet, and infrared observatories, instruments that can capture the fleeting signatures of molecular survival in the most violent environments in the universe. Particles accelerated inside these stellar explosions reach energies that rival some of the most powerful sources in the universe. For decades, the standard model of solar flares assumed that the highest energies reached by accelerated electrons and protons topped out at a few 100 million electron volts. That limit came from the strength of the magnetic reconnection region and the time available for acceleration before the flare died out. But a new generation of space-based gamma-ray telescopes, including the Fermi Gamma-Ray Space Telescope, has found flares on other stars that smash through that ceiling. These events produce hard X-rays and gamma rays at energies of billions of electron volts, sometimes even tens of billions, far above what any solar flare has ever achieved. The spectra from these extreme flares do not follow the simple power law decline predicted by standard shock acceleration models. Instead, they show a distinct hardening at the highest energies, a signature that something beyond ordinary magnetic reconnection is at work. The leading candidate is a mechanism called diffusive shock acceleration, where a relativistic shock wave, moving at a significant fraction of the speed of light, repeatedly bounces charged particles across its front, boosting their energy with each crossing. Such shocks can only form in the most violent reconnection events, where the magnetic field energy is released almost instantly in a very small volume. Another possibility involves magnetic reconnection in a regime called the strong guide field limit, where the magnetic field lines are twisted to an extreme degree. In that environment, the reconnection region can generate electric fields strong enough to directly accelerate particles to relativistic energies in a single pass. This is not the gradual process seen on the Sun. It is a lightning strike inside the star's atmosphere, a bolt of electromagnetic force that kicks electrons and protons to near-light speed in microseconds. The discovery has forced particle acceleration theorists to rework their models because the standard assumptions about the maximum energy a flare can generate are clearly too low. And it carries a deeper implication. These high-energy particles, once accelerated, can escape the star's magnetic field and travel through interstellar space. Over millions of years, countless flares across the galaxy may have seeded the cosmos with a population of high-energy protons and electrons that we now detect as cosmic rays. The link between stellar flares and cosmic ray origins, once only a hypothesis, is gaining real support from these extreme spectra. Each new observation of a flare that breaks the energy record sharpens the picture, showing that even ordinary stars, when they erupt in the right way, can contribute to the most energetic particles in the universe. But some stars do not stop at one eruption. A star that erupts once is dangerous. A star that erupts dozens of times in a single day is something else entirely. The Transiting Exoplanet Survey Satellite, or TESS, has caught many M-dwarf stars in the middle of what astronomers call flare storms. In these events, a star unleashes not a single burst but a cascade of flares, sometimes more than 100 in just a few hours. Each flare follows so quickly after the previous one that the star's brightness never fully returns to normal before the next explosion begins. The light curve looks like a jagged sawtooth, a continuous series of spikes with no quiet gaps. This pattern challenges one of the most basic assumptions about how flares work. For decades, scientists treated each flare as an independent event, a local magnetic instability that released its energy and then faded away, leaving the rest of the star unaffected. But a flare storm suggests something far more connected. The energy from one eruption does not simply dissipate. It seems to ripple through the star's magnetic field, destabilizing neighboring regions and triggering new reconnection events. The star becomes a chain reaction factory, where one explosion sets off the next, and the next, and the next, until the entire magnetic field appears to be trembling. Test data on some of the most active M-dwarfs, like the star known as Proxima Centauri, show that during a flare storm, the intervals between flares can shrink to just a few minutes. The energy released in one outburst appears to shake the magnetic field lines elsewhere, twisting them or pushing them past a threshold of stability. It is as if the star's magnetic field is a single, interconnected web, and a snap at one point sends vibrations along the entire network, causing other sections to break in turn. This picture of global magnetic instability forces a rethink of how magnetic energy is stored and released across a star's surface. Instead of isolated pockets of stress, the whole corona may enter a state of heightened sensitivity during a storm, where any small disturbance can trigger a major eruption. The implications for space weather around such stars are severe. A planet orbiting an M-dwarf in the middle of a flare storm does not face a single blast of radiation followed by quiet recovery. It faces a relentless pounding. The atmosphere has no time to cool or rebuild between outbursts. Each new flare arrives while the previous shockwave is still reverberating through the planet's magnetic field. The cumulative effect over just a few hours can strip away far more atmospheric gas than the sum of the same number of isolated flares. Models show that repeated irradiation at short intervals can heat the upper atmosphere to temperatures that drive an accelerated escape, a kind of boiling off that does not stop when the storm ends, because the gas is already so hot that it continues to leak away. This turns a flare storm into a kind of atmospheric eraser, capable of transforming a potentially habitable world into an airless rock in a single night of stellar rage. But the storms also reveal something deeper about the star itself. The onset of a storm often follows a long period of quiet, as if the magnetic field is slowly building tension over weeks or months. Then, suddenly, it all comes apart at once. This behavior mirrors some models of self-organized criticality, where a system slowly accumulates stress and then releases it in a cascade of events that obey a power law. In that view, a flare storm is not a random fluke. It is the natural consequence of a magnetic field that has reached its breaking point, the way a sandpile suddenly avalanches when it becomes too steep. Some stars may experience these storms regularly, maybe once every few weeks, while others may go years between them. The challenge is to predict when a star is about to enter a storm, because the warning signs might be subtle: a slight increase in the number of small flares, a change in the pattern of spot coverage, or a shift in the star's overall brightness. If astronomers can learn to read those signals, they could warn future space missions about which systems are safe to study and which are too volatile. For now, every new TESS observation of a flare storm adds another piece to the puzzle. The data show that these cascades are not rare. They occur on many M-dwarfs and even on some Sun-like stars, though less frequently. The storms force us to see stellar magnetic activity as a collective phenomenon rather than a collection of isolated events, and they raise a haunting possibility. Could our own Sun ever experience a flare storm? No storm of the scale seen on M-dwarfs has ever been recorded in the thousands of years of solar observation, but the models suggest that if the Sun's magnetic field were ever stressed enough, a cascade could begin. The consequences for Earth would be immediate and widespread. Satellites would fail, power grids would overload, and communications would collapse under the repeated assault. The sky would shine with artificial aurorae from pole to pole, not because of a single storm, but because a whole series of storms kept the planet's magnetosphere in a constant state of agitation. That scenario remains hypothetical, but the discovery of flare storms on other stars reminds us that the rules of stellar behavior are not as fixed as we once believed. The same magnetic laws that create a quiet, predictable sun can, under the right conditions, produce a star that simply will not stop erupting. And that is a lesson written in the jagged light curves of distant red dwarfs, a warning that a star's temper can sometimes be a chain reaction. But some chain reactions do not end with the flares themselves. They leave behind a shadow. Astronomers have recorded a strange and unsettling pattern in the light curves of certain stars. A powerful flare erupts, a brilliant spike of energy that fades over hours. Then, unexpectedly, the star grows fainter, not by a tiny amount, but by a deep, prolonged dimming that can last for days or even weeks. This drop in brightness is far too large to be explained by a normal star spot rotating across the surface. A spot might dim a star by a fraction of a percent. These dimming events can reach several percent, sometimes 10% or more, and they always follow a flare. The connection is clear, but the cause is a riddle that has divided astronomers. One leading idea is that the flare itself hurls a massive cloud of material into space, and that cloud, made of gas and dust, temporarily blocks a significant portion of the star's light. On our Sun, coronal mass ejections are mostly invisible because the material is thin and hot. But on other stars, especially cooler ones, the ejected material might be dense enough to contain solid particles, tiny grains that condense as the cloud expands and cools. These grains would scatter and absorb starlight, creating a dimming that could last until the cloud disperses. The geometry matters. If the cloud is launched directly toward Earth, the dimming would be deep and brief. If it moves sideways, the dimming might be weaker but last longer. But there is another, more violent explanation. The flare might have shattered a planetesimal. A planetesimal is a small rocky or icy body, a building block of planets that orbits the star. If a flare is powerful enough, and if a planetesimal happens to be in the wrong place at the wrong time, the intense radiation and particle bombardment could fracture it into countless fragments. Those fragments would form a temporary debris cloud, a ring of dust and rubble that orbits the star and blocks its light as it passes. The dimming would be irregular, changing over days as the cloud spreads and thins. The most famous example of this mystery is a young star named RAK 210. This star, located in a star-forming region about 400 light-years away, has been observed to undergo repeated, deep dimming events that last for several days. The dimmings are not periodic, they do not match the star's rotation, but they are often preceded by a flare. Researchers have studied RAK 210 across multiple wavelengths. In visible light, the dimming is so severe that the star sometimes fades by nearly 15%. In infrared light, the dimming is weaker, which suggests that the material blocking the light is made of small dust grains, because dust tends to scatter blue light more than red. That is exactly what you would expect from a debris cloud, whether from an ejected semi or a shattered planetary body. The challenge is telling them apart. If the dimming is caused by a flare-launched cloud, the cloud should be moving away from the star, and its dimming signature should change over time as it expands. If it is caused by a shattered planetesimal, the debris would remain in orbit around the star, and the dimming might recur at regular intervals as the debris cloud completes its orbit. For RAK 210, the dimmings do not repeat at a fixed period, which leans slightly toward the ejected cloud idea, but the data are not conclusive. Other stars show similar behavior. The Kepler telescope found several cases where a superflare was followed by a slow, deep dimming that took weeks to recover. In those systems, the dimming sometimes appeared only once and never returned, suggesting a one-time event like a planetesimal destruction. In other cases, the dimming repeated years later, hinting at a persistent debris ring. The mystery cuts to the heart of how we understand a star's environment. When a flare erupts, we now know it can do more than heat plasma and accelerate particles. It can physically reshape the material around the star. It can lift dust, destroy worlds, or cast shadows that last for weeks. And those shadows tell a story we are only beginning to read. The connection between a flare and the darkness that follows remains one of the most open questions in stellar astrophysics, a puzzle where each new observation seems to deepen the mystery rather than solve it. For every answer we find, another question rises from the dust. The strangest flares of all may point to something invisible, not just through the shadows they cast, but through light that should not exist. A small but growing number of theoretical physicists have proposed that some stellar flares might not be magnetic at all. They might be caused by particles of dark matter. This idea sounds like science fiction, but it is built on serious mathematics. The particles in question are called actions, or more broadly, action-like particles. These are hypothetical lightweight particles that are among the leading candidates for dark matter, the mysterious substance that makes up most of the mass in the universe. Theory says that inside a star's core, where temperatures and densities are extreme, actions could be produced in abundance. They would have almost no mass and interact so weakly with ordinary matter that they would stream straight out of the star, escaping the core and the surrounding layers without ever bumping into anything. But here is where it gets interesting. In the presence of a strong magnetic field, a small fraction of those actions can convert into photons, particles of light. That conversion would happen most efficiently exactly where magnetic fields are strongest, which is also where stellar flares happen. If actions are real, then a star like our Sun would be steadily emitting a faint glow of converted photons from its entire magnetically active volume. That glow would add a small, constant background to the star's normal light, but during a flare, when the magnetic field is briefly amplified and twisted to extreme levels, the conversion rate could spike dramatically. The result would be a sudden burst of extra light, a false flare that looked exactly like a real magnetic eruption, but whose origin was a cloud of dark matter particles turning into photons in the magnetic chaos of the reconnection site. The challenge is telling the difference. A dark matter flare would have a distinct signature in its spectrum and in its timing, because action conversion depends on the magnetic field strength in a very specific way. The energy of the converted photons would cluster in a narrow band rather than spreading across the full range of a typical flare. It might also show a slight delay relative to the peak of the magnetic activity, because the actions are produced deep in the star and take a measurable time to reach the surface. Several research groups have searched for these signatures in solar data, but the signal is tiny and buried under the overwhelming noise of the Sun's ordinary flare activity. So far, no definitive detection has been made, but the upper limits have already ruled out the simplest versions of the theory. However, more complex models remain possible. The true test might come from other stars. If actions exist, their production rate scales steeply with temperature, so a hotter star would produce far more actions than the Sun. And its magnetic activity would be correspondingly more intense. Some astronomers have proposed that the most puzzling superflares, especially those that do not fit the standard magnetic models, could be candidates for action conversion events. These would be flares that show an excess of high-energy emission in a narrow energy range, or that appear without any clear magnetic precursor. The idea is highly controversial. Many astrophysicists remain skeptical, arguing that the observed flares can still be explained by conventional magnetic processes once the complexity of stellar dynamos is fully accounted for. But the implications, if proven true, would be revolutionary. A stellar flare would no longer be just a magnetic storm. It would be a window into the dark universe, a place where the invisible particle that fills the cosmos briefly becomes visible as a flash of light. That would transform the study of flares from stellar weather into fundamental physics, turning every star into a dark matter detector. It would open a direct channel to the most elusive substance in the universe, one that has so far been detected only through its gravitational pull. The strangest discovery of all, then, might be that the same explosions that shape planets, strip atmospheres, and reveal hidden magnetic fields also hold the key to understanding the missing mass of the cosmos. The search is just beginning, and if a star ever erupts with light that cannot be fully explained by any known magnetic process, it might be telling us something profound about the nature of reality itself. These 25 discoveries paint a portrait of stars far stranger than textbooks ever described. Each finding chipped away at the old assumption that stars are simple, steady spheres with predictable magnetic storms. Instead, we see a universe where a single flare can outshine an entire star, where magnetic fields lock into permanent patterns, where planets trigger their own suns to erupt, and where the line between a stellar explosion and a dark matter signal blurs into possibility. The textbook image of a star as a calm, reliable fusion engine is gone. In its place stands something far more alive, restless, and capable of surprises that range from the creation of molecules in million-degree plasma to the launching of clouds that cast shadows for weeks. The study of stellar flares has become a gateway to extreme physics. It connects the smallest scales of particle acceleration to the largest scales of planetary destruction and creation. It touches on the origins of elements, the fate of atmospheres, the rhythms of binary companions, and even the nature of the invisible dark matter that fills the cosmos. Every new telescope, from Kepler to TESS to the upcoming observatories, adds another layer to this story, and every layer reveals that we are only scratching the surface of how stars behave. The sun we depend on, the stars we gaze at, they are not peaceful lanterns. They are engines of violent change, shaped by forces we are only beginning to understand. If any of these discoveries left you with a lingering question or a sense of wonder, you are not alone. The mystery of stellar flares is far from solved. That is why each new observation matters, and why the search for the next strange discovery continues. If you want to follow that search, consider subscribing to join future deep dives into the unknown corners of the cosmos. And in the comments, let us know which of these 25 findings surprised you most, or what strange stellar behavior you would add to the list. The universe is full of stories written in light. We are just learning to read them.